Hi, I'm Kim from Captis Aire, my spin-out company. I'm excited to share with you my poster, Transforming Emissions Control Using a Fluidized Bed Concentrator and Bead Activated Carbon. The problem with emissions control devices is they use oxidation to burn up the emissions. This uses a tremendous amount of energy, creates greenhouse gas emissions, and is very expensive to operate. The alternative is to very efficiently adsorb and recover those same emissions. Now, this technology could be literally deployed in over 100 devices today to reduce energy usage by over 10 trillion BTUs, drive down operational costs, and generate revenue by transforming what would have been pollutants into valuable byproducts. So it's good for industry, and it's good for our air. Our objective is to transform the emissions control technology business. We have both a short-term and a long-term strategy. Short-term, we want to reduce energy usage in emissions control devices that are required in wood drying operations, such as the wood pellet and oriented strand board manufacturing sites. You can see the many sites that are available for this technology on this map. Commercializing this technology at just 50 of these sites could enable us to reduce energy usage by over 10 trillion BTUs per year, reduce carbon intensity by over 1 million tons per year, and generate 15 million gallons per year of biofuel. Long term, there are over 100 segments of the chemical industry that could utilize this technology. Beyond that, there may also be applications in the energy sector, specifically coal mining, as well as agricultural applications. So this one slide really demonstrates the transformational capability of the FBC, that's the Fluidized Bed Concentrator, as compared to the RTO, that's the Regenerative Thermal Oxidizer. In this particular case study, the RTO used as much as 10 times as much energy as the FBC. And that's driven primarily for two reasons. One, the operating temperature difference, and two, the media configuration. Here you can see that the RTO is operating at over 1400 degrees Fahrenheit to burn up the emissions. By contrast, the FBC adsorbs those emissions at about 175 degrees Fahrenheit. We then heat that media to about 400 degrees Fahrenheit to regenerate it. This demonstrates that we can reduce the operating temperature as compared to the RTO by over 1,000 degrees. We also have a significant media configuration advantage. In the RTO, they use these ceramic saddles that are very brittle. It takes about 8 feet of media in the RTO, and there's 2 beds, so 2 times 8 is 16 feet of total media depth through which that process air has to be passed. By contrast, in the FBC, there are 6 trays of fluidized media, and each tray is about 2 inches deep for a total of about 1 foot of fluidized media, as compared to 16 feet of static or non-moving media in the RTO. This means that the differential pressure across the adsorber in the FBC is significantly reduced as compared to the pressure across the RTO. Our pressure is about 3.5 inches as compared to 10 to 20 inches in the RTO. This variation is due to varying degrees of plugging that can occur in the RTO. So this means that we can use a 300 horsepower fan as compared to a 1200 horsepower fan in the RTO, which drives the electrical savings. Also, as there are 2 beds in the RTO and there's only 1 bed in the adsorber, that means that our system is approximately half the size as compared to the RTO. This means less steel and less weight, as well as a smaller footprint. Also, our media is bead-shaped. It looks much like a poppy seed, and it flows very much like water. This means that if there needs to be any cleaning or maintenance done to the device, we can easily drain the media out of the system, do whatever maintenance is required, then replace the media. By contrast, in the RTO, they have this very brittle ceramic saddle. And when they need to do cleaning and maintenance, they have to have operators literally climb inside the RTO. To remove it, they vacuum it out. When they vacuum it out, it breaks the media, which means they have to discard it, buy new, and then replace it. Also, the FBC is inherently safer than the RTO for several reasons. First of all, the operating temperature reduction. Two, the fact that our device has no large, heavy moving parts. In fact, the only moving parts in our device are the fans, which move the carbon through the system. Finally, as I already described, the cleaning and maintenance is significantly easier on the FBC as compared to the RTO. So the great thing about the FBC, it's already been commercialized in applications such as automotive paint spraying, but it's never been used for controlling emissions from wood drying. Wood drying has its own special challenges. For instance, the moisture content, the temperature, and the particulate loading of the air are relatively high, and these present unique challenges for treating the air, especially with a carbon media. We tested the effectiveness of this technology in 3 stages. First in the lab, second in a trial with a pilot unit in 2017 at a commercial-oriented strand board manufacturing site where we demonstrated the emissions control capability. Then in 2018, we ran a much larger, much more comprehensive trial, again at the commercial-oriented strand board manufacturing site. In 2018, we were online for over 1,700 hours over a period of about 6 months. Now I'm going to play for you a short animation that describes how this technology works.
Now let's look inside. Process air containing emissions enters the adsorber. It passes up through a series of trays filled with activated carbon beads. Just like the carbon or charcoal you probably use in your house to clean your drinking water, activated carbon cleans the air. When the emissions hit the carbon, it very efficiently adsorbs those emissions. Then the clean air exits out the top of the adsorber. The carbon falls to the bottom of the adsorber and is transported using air from the fan to pneumatically convey it to the desorber. In the desorber, the beads are heated to release the emissions. At the same time, nitrogen gas is moved across the carbon to sweep the emissions in vapor form to the condenser. The carbon moves to the bottom of the desorber and is conveyed pneumatically back to the adsorber, where it is reused again to adsorb the emission. In the condenser, the vapors hit the very cold surfaces of the tube and shell style condenser to convert the vapors to liquid. The liquid is then collected and sold. Finally, a small amount of carbon is continuously fed to the side stream reactivator, where it is heated to over 1400 degrees Fahrenheit to remove any residual traces of organics that might accumulate on the carbon. This ensures the carbon remains clean enough to continue to adsorb the emissions effectively. Here you can see what the beads look like when they are fluidized in the trays. When the air blows through the holes in the trays that are full of beads, it fluidizes them, which makes them look a little like they are boiling.
One of the successes of our 2018 pilot trial was the fact that we collected terpenes. Terpenes are the primary constituent of the sap of pine trees, such as southern yellow pine. And they're the primary component of the emissions that are driven off the wood when it's dried. So when we adsorbed, desorbed, and collected the emissions, we collected these terpenes, which are primarily alpha and beta pinenes. These terpenes are responsibly recovered, bio-based materials, and they can be sold as fuels, fragrances, solvents, etc. At the end of the pilot trial, we tested the emissions control effectiveness. The PCWP max standard requires a greater than 90% reduction efficiency. And I'm very happy to say that we demonstrated this greater than 90% reduction efficiency twice using 2 separate certified air emission stack testing companies. On this particular day, we demonstrated this 3 times in a row in each of the 3 one-hour tests. We took these results and reviewed them with both state and federal environmental agency personnel. In every discussion, environmental agency personnel were supportive for permitting for a full commercial system. We also demonstrated over 80% reduction in energy and carbon intensity. Here you can see we used no natural gas, and we reduced electricity usage by over 40%. We also reduced the carbon intensity by over 80%. So what this means for the user is we finally have the opportunity to drive down operational costs of their emissions control device. This chart demonstrates that the long-term capital and operating costs of the FBC as compared to the RTO are almost half over a period of 20 years. So our pilot trials were very successful. We reduced energy usage by over 80%. We met the MAC PCWP requirement of over 90% reduction efficiency on the emissions. We demonstrated good operational reliability and safety. And our next step is to commercialize this technology by scaling up to a full-size commercial system. We're talking with a number of wood pellet manufacturers today and look forward to taking this final step. Here you can see our timeline. It'll take us about 6 to 12 months to fabricate and install the device. Then we'll take about another 3 to 6 months to demonstrate long-term operational reliability, optimize the system, and do our final economic and commercial validation. I'd like to thank Georgia Pacific Chemicals, our patent owner, from whom we are licensing this technology, as well as Environmental CNC, our equipment and technology provider. Hal and his team at Environmental CNC have been fantastic partners over this past 5 years during which we've been doing this project. This team has the necessary capabilities, integrity, and passion to deliver. Thank you.